Hello everyone, this is Mr. Zimmerman, and today we're going to look at the last section that we're going to do in Chapter 7, which is 7-5. So let's take a look at this box at the top of the page first. It says, a scale drawing is a drawing of an object that is smaller or larger than the actual object, and that the drawing scale, which is really the same thing as the scale factor we've been talking about in Chapter 7, is the ratio of any length that we know in the drawing to the corresponding actual length of the object. The scale that we're given, or the scale factor for the diagram of the doghouse that we have here, is that 1 inch in the drawing is 3 feet in the actual doghouse. So then it says find the length of the actual doghouse. So we are going to set up a ratio using the scale that they gave us. So 1 inch in the drawing is the same thing as 3 feet on the actual doghouse. And then you can see that they've given us 0.75 inches here. And so we're going to set that up so that when we set up our proportion, our second fraction is also going to be inches over feet. And then we have 0.75 inches on the top, and we're going to put X feet on the bottom. Now we'll just do our cross product. So we'll do 1 times X, that's just X, is equal to, and then our other cross product, we have 3 times 0.75, which is 2.25. And we can see that we were trying to solve for X here, and X was in feet. So our answer will be in feet. So that is the length of our actual doghouse. Now let's take a look at example 1, and let's do, I don't think we need to do all 4 of these, but let's do a couple of the problems in example 1. In the example above, we were giving the scale, and then we were going to try to find the actual length of the doghouse. This time we're going to go the other way around. They're going to give us the actual dimensions of a room, and then we're going to have to find out, well, how big would those, how big would the length and the width be on the scale drawing? It says that we have a rectangular fitness room in a recreation center that is 45 feet long and 28 feet wide. And it says find the length and width for a scale drawing of the room using the following scales. So we're going to do this more than once. I think for this one, let's just do number 3 and number 4. So first of all, let me draw you a little picture of this one. So here's just a quick sketch. Again, it's a rectangular room. These are the actual dimensions. The length is 45 feet and the width is 28 feet. And then we want to find out how big would that room be represented by in the scale drawing. So let's do number 3. Let's start out by making a ratio out of our scale. So our scale factor is 1 inch in the drawing is 3 feet in the actual room. And we're going to set up our proportion here. So first, let's find the length of the room on the scale drawing. So the length of the actual room was 45 feet. And let's put our X here. That's going to be in inches. So both of these are set up as inches over feet. Now let's do our cross products. So we're going to go 3 times X equals 1 times 45, divide both sides by 3, and we get X equals 45 divided by 3, that's 15. And again, our X here, that was given, or we were solving for X in inches. So our units would be inches. So that would be the 45 feet in the actual room using this scale would be 15 inches. Would be the length on the scale drawing. Now we have to do the same thing to find the width on the drawing. So again, we're going to use the same scale. So we know they have 1 inch on the drawing is the same thing as 3 feet in the actual room. And that's going to have to equal. And again, this one's also going to be in inches over feet. Now we have 28 feet in the actual room, and we're going to solve for how many inches that is on the drawing. So I'll call that X. Doing our cross products, we have 3 times X. That'll give us 3X equals. And we have 1 times 28 is 28. Then we divide both sides by 3. And this time we get X is equal to, well, it comes out to be 9.3 repeating. And that's the same thing as 9 1/3. All right, again, we're solving for X in inches here. So that 9 1/3 would be in inches. And that would be the same thing as our width. That's the width on the drawing. Again, so 28 feet in the actual room would be 9 1/3 inches on the drawing. Let's move on to number 4. The first thing we have to do on number 4 is look at our scale factor. Our scale here is 1 inch is 6 feet 8 inches. All right, so 1 inch on the drawing is 6 feet 8 inches in the actual room. And then, so we have these mixed units here. I'd like to change these all into feet. So we have 1 inch in the drawing, and then we have 6 whole feet, but then we also have 8 inches. Well, 8 inches, that's 8 inches. Well, a foot is 12 inches. So that's 8 inches out of 12 inches. Well, if you do 8 divided by 12, that would be the same thing as 2/3. So we would have 6 2/3 feet. But I don't really want to do this problem with fractions. So let's see, 1 inch then on the drawing would go with 6 whole feet. And if you do 2 divided by 3, that's actually 0.6 repeating. But I don't want to use for the repeating part of this decimal. You guys know that that means 0.666666. Well, I'm gonna round that off. So I'm gonna go with 1 inch to 6.67 feet. And then I think that'll make this problem a lot easier. So let's set up our ratios and our proportion. So 1 inch then on the drawing is the same thing as 6.67 feet in the actual room. And you can't see it here, but then the other dimensions we had, again, this one's also going to be inches over feet, is we were looking for the number of inches on the drawing that would correspond to a length of 45 feet in the actual room. Next, let's do our cross product. So we would have 6.67 times x equals 1 times 45, which is 45. Now we'll just divide both sides by 6.67. Now, if you want to get a more accurate answer, when you type this in your calculator, you could do 45 divided by, and you could type in 6.66666, type in a bunch of sixes. I typed it in just like we got it, and we ended up with x equals, what have I got here? 6.7466. And I think I would probably round that off right there. So after that 4, I have a digit that is 5 or greater, so I'm going to round this up to 6.75. And again, the answer we were looking for here, this would be x in inches right here. So this would be inches. And again, that would correspond to the length in the drawing. So I'll set that equal to my length. So we ended up with 45 feet in the actual room. That would correspond with 6.75 inches on the actual drawing. Now we have to do the same thing for the width of the room. So again, our scale this time is going to be, we're going to use 1 inch over 6.67 feet. And again, we're going to set up this other ratio as inches over feet. And this time we're going to have a width of 28 feet. And we're going to have X inches on the top. Let's set our cross products equal again. So we're going to have 6.67 times X is going to equal 1 times 28. Then we're going to divide both sides by 6.67. And we get X equals 4.1979, which I'm going to round off again to the nearest hundredth right here. Since that number after the 9 is 5 or larger, I'm going to round that up. So I am going to get 4.20. And that is going to be the width in my drawing. I guess I should put units on that. So the width on my drawing is 4.20 inches. Let's move on to the next page and look at the box at the top of the next page. We have the proportional perimeters and areas theorem. And what it says is if two figures are similar and their similarity ratio or their scale factor is A to B, then the ratio of their perimeters is also A to B, and the ratio of their areas is A over B squared. So let's take a look at the example in the box here to see how this works. So looking here first, they're setting up the ratios of the corresponding sides. And they're doing it the side lengths in the large triangle divided by the side lengths or the corresponding side lengths in the small triangle. So what they do here is they say they have 9 over 3, those two sides correspond, and then they have 15 over 5, and then they have 12 over 4. And each of those fractions, if you reduce them, they're all equal to 3 over 1. Well then, let's do the perimeters of both of these really quick. So on the big triangle, we would have 9 plus 15 is 24 plus 12. That will give us a perimeter of 36. And then for the small triangle, we'd have 3 plus 5 is 8 plus 4. That would be 12. So if we do the ratio of the perimeters, again, using the large triangle over the small triangle, we have 36 over 12, which is 3 over 1. So we can see that when we do the ratio of the corresponding side lengths, we get 3 over 1. But then when we do the ratio of the perimeters, we also get 3 over 1. Then in the next part of the theorem, they set up the ratio of the areas. Well, in order to find the area of a triangle, you have to do the base times the height, and those have to be perpendicular, okay? They have to form a right angle, and then you have to divide by 2. So in the large triangle, the base would be 12 and the height would be 9 because there's your right angle. Those have to be perpendicular. So you would do 9 times 12 and then divide it by 2. So you would get 54. And for the area of the small triangle, the base of the small triangle would be 4 and the height would be 3. So you do base times height would be 4 times 3, which is 12. Divided by 2, and that would give you 6. So the ratio of the areas, again, doing the large triangle over the small triangle, is 54 over 6. And if you divide the 54 by 6 and the 6 by 6, you reduce that fraction to 9 over 1. Well, 9 over 1, if you look carefully, is 3 over 1 squared. So the conclusion of this proportional perimeters and areas theorem is that the ratio of the perimeters is the same as the scale factor, and the ratio of the areas is the same as the scale factor squared. Now let's move on to example 2, and let's try a couple of these problems. In number 5, we're given that these two triangles are similar, so we have to have that first. And then let's go ahead right away and let's set up our scale factor. So our scale factor on this one, let's use 9 in the small triangle. That corresponds with 12 in the large triangle. So let's set up a ratio using that. We have 9 in the small triangle corresponding with 12 in the large triangle. So that is our scale, or our scale factor. And we're going to set that equal to, well, we know the perimeter of our small triangle right here is 30 inches. So that's going to go on top. So it's going to give us 30 over, and we're solving for the perimeter of the large triangle, so let's call that P. Now we can solve this proportion exactly like it is, or we could reduce this to get our reduced form of our scale here, or our scale factor. So on that one, let's go ahead and do that. So 9 over 12, that's going to reduce to 3 over 4. So we're actually going to have 3 over 4 is equal to 30 over the perimeter of the large triangle. Let's solve that one. The numbers will be a little bit smaller for us. Doing our cross products, we have 3 times P equals 4 times 30 is 120. We'll divide both sides by 3. And we'll get the perimeter of our large triangle is equal to 40. And since the units in this problem are in inches, our perimeter would be in inches. Well, the other thing we have to do with this one is we need to find the area of the large triangle. So in order to do that, we're going to use our same scale factor again. So that's going to be 3/4. But remember now, when we set up this proportion to solve for the area of the large triangle, we need to square our scale factor. So we're going to square the 3/4. So it's 3/4 squared. That is going to equal, remembering that we set this one up as the ratio of the side lengths in the little triangle over the big triangle. So we would put the area of the little triangle on top, which is 36, and we would divide that by the area of the large triangle, which we'll call A. Squaring 3/4, that would be 3/4 times 3/4. So we have to square the numerator, so 3 squared would give us 9, and 4 squared in the denominator would be 16, and then that would equal 36 over A. Doing our cross products, we would have 9 times A, so 9A equals, and then we would have 16 times 36, which is 576. Then we would divide both sides by 9, and we will get A is equal to 64. Now, since our units in this problem were, again, inches, that area would be in square inches, or inches squared. So by using our scale factor set up as the ratio of our corresponding sides, we were able to figure out the perimeter of the large triangle and also the area of the large triangle. Let's move on to number 6. In number 6, we're given that we have 2 rectangles that are similar, and then we're going to do the same process. We got to find the perimeter and area of, at this time, the small rectangle. In example 5, we set that one up as a little triangle over big triangle. Let's go the other way this time. So we're going to set up our ratio of corresponding sides. We have 21 in the large rectangle corresponding to 14 in the small rectangle. So let's set up our scale factor, this time using 21 in the large rectangle corresponding with 14 in the small rectangle. So we set up our scale or our scale factor for this one again as we set up the ratio as being the side length in the large rectangle divided by the side length or corresponding side length in the small rectangle. And then we should probably go ahead and reduce that fraction. So if we divide the numerator and denominator of our scale factor by 7, we will have a scale factor of 3/2. So let's go ahead and find the perimeter of our small rectangle. And we can see inside the large rectangle, the perimeter is given right here as 72 centimeters. So we're going to set this one up. We're going to use our scale factor of 3/2. That has to equal the perimeter in the large rectangle, which is 72, divided by the perimeter of our small rectangle, which is what we're trying to solve for. Doing our cross products, we have 3 times p, so that's 3p, equals 2 times 72, which is 144. Then we'll divide both sides by 3. And we'll get the perimeter of our small rectangle is 48. And looking at the units in this problem, the perimeter is in centimeters because the side lengths are in centimeters. So let's add centimeters on there for our units. And there you go. We have the perimeter of our small rectangle. Now let's move on and find the area of the small rectangle. Now we use the same scale factor again of 3/2, but remembering that to get the ratio of our areas, we have to square that number. And since we're doing this one large rectangle over small, on the top we would have the 315 square centimeters as the area of the large rectangle, divided by the area of the small rectangle, which we will call A. Squaring our scale factor, we have 3 squared, so that's 3 times 3 is 9. And in the denominator, we have 2 squared, which is 2 times 2 is 4. That's going to equal 315 over the area of our small rectangle. Our first cross product is 9 times A, and that will equal 4 times 315, which is 1,260. Then we'll divide both sides by 9, and we'll get area of our small rectangle is 140. And we can see that our units for our area was, well, our side lengths are centimeters, so our area is going to be in square centimeters. So centimeters squared. And there we have it. I think that's enough examples for section 7-5. Once again, thanks for watching, and I'll see you soon in class. Thanks. Bye.